The graph looks very similar to what we had before, but let's keep in mind that what we're actually graphing on the horizontal axis is time now rather than position. Again, the point is going to be going up and down to a maximum value that is still the amplitude. So our variation from equilibrium to maximum is still A, the amplitude. But what is the distance, so to speak, from peak to peak? What is this now? Well, it's not the wavelength because we're actually measuring time. How much time does it take for the wave to go from a maximum value, remember, as it's passing us by, from a maximum value to the minimum and back to maximum? That's what we call the period of the wave. Because remember, we're talking about how much time this is taking. And the period we will write with a capital letter T. So T, the period. What are the units? Well, it's a time. It's a measure of a time. So the standard SI units for period will be seconds. The period tells us how much time does it take for one complete wave to pass us. Okay, great. Let's go back to the drawing of the wave like a snapshot. Imagine you take a picture of the wave. Let's go back to the drawing of X just for a second. So here I've redrawn the first plot, where basically you can think of this as a kind of like a picture of the wave. Well, maybe a picture if this were actually physical displacement, but a graph of the density or something like that at one instant of the wave. Now, let's imagine that we've got some wavelength here. This is, again, a measure of the wavelength. And let's imagine that for our wave here, we have a wavelength of, let's say, 3 meters. Over here, as we watch these waves pass by, let's imagine that we measure a frequency of 10 hertz. In other words, 10 waves pass us per second. Well, how much wave will have passed us in 1 second with these numbers? Let's think about that. In 1 second, 10 waves will have passed us with a frequency of 10 hertz, 10 waves per second. In 1 second, 10 waves will have passed us by. Each wave is 30 meters long. Well, 10 waves, 3 meters long, sorry, 3 meters long. 10 waves, each of 3 meters, means that 30 meters of wave will have passed by us in 1 second. Well, if 30 meters pass us in 1 second, the wave must be moving at 30 meters per second. How do we get 30? Well, it's F times lambda. And what's this? That's the speed of the wave. This is a very, very general result that the wavelength times the frequency of the wave is equal to the speed of the wave, which we will call v. This is a very general result that applies to all sorts of different kinds of waves. The wavelength of the wave times its frequency is equal to the speed of the wave. Okay, very, very good. Let's stick some numbers in here. If you have a particular favorite radio station, I was just talking to a class of mine, and nobody even listens to the radio anymore. Most people listen to music on their computers. But let's imagine that you have a favorite radio station, and let's figure out what's the wavelength of a radio station. Personally, I like listening to classic rock, and here in Atlanta, I listen to The River, which is 97.1 on the FM dial. But what does that mean? 97.1, what does that mean? It's actually telling us the frequency of the wave. And what are the units? So this is the frequency. And what are the units? An FM, that's megahertz. So 97.1 megahertz. In other words, the frequency for this particular radio station is 97.1 times 10 to the 6th hertz. Megahertz, million hertz. So 97.1 times 10 to the 6th hertz. Well, what's the speed of the wave? Well, radio signals are a part of the electromagnetic spectrum. They are very long wavelength waves, longer than visible light, but they still travel at the speed of light in a vacuum. Waves in the atmosphere travel slightly slower, but let's just take a look at, in the atmosphere it's almost the speed in a vacuum, so we'll just use the speed in a vacuum. The speed of electromagnetic waves is such an important number and comes in so many different places, it's got its own symbol. Have you ever heard of the equation E equals mc squared? Probably the most commonly known equation from physics. Well, c in that equation means the speed of light, or the speed of electromagnetic waves. And in a vacuum, it has approximately the value 3.00 times 10 to the 8 meters per second. Let's see if we can figure out what's the wavelength of the river's radio signal given a frequency of 97.1 times 10 to the 6th hertz at a speed of 3 times 10 to the 8th meters per second. Well, we know the wavelength. We know lambda f equals c, or lambda equals c over f, which is 3.00 times 10 to the 8th meters per second, divided by the frequency, 97.1 times 10 to the 6th hertz. Divide that out, and what do we get? We get 3.09 meters. That is the wavelength of the wave. Unfortunately, I do not have 3.09 meters of space that you can actually see on my whiteboard here, but starting here, going all the way over to here, that's 1 meter, going again 2 meters, again 3 meters, and then to here, that's 9 centimeters, 3.09 meters. That's how long, if you can just imagine, okay, 1 meter, 2 meters, 3 meters, 3.09 meters. That's the length, the wavelength of the signal from the river 97.1. Just as an aside, I mentioned this is an FM radio station. What is the difference between FM and AM? Let me just very quickly write this down. So FM stands for frequency modulation, while AM stands for amplitude. That capital A. Modulation. And that tells us how they actually encode the signal, the voices, the music, or whatever, into the radio wave so that you can then, say, decode that with your radio or whatever on the computer. So FM, they vary the frequency of the wave. So if you've got this particular wavelength, if you vary this wavelength slightly as you send out the wave, that can then be received by the radio and translated into the sound somehow. If you modulate or change the amplitude, in other words, so you've got a wave going like this, if you change how much it goes up and down, sometimes large or sometimes small, that's a greatly exaggerated situation, but you maybe make it oscillate a little bit sometimes, and you oscillate it more sometimes. You can incorporate the information into the amplitude as you send out the signal. And just one more interesting difference here. For FM, I said the units were megahertz. Well, for an AM station, if you know what the frequency of the AM station is, those units are kilohertz. So if you like to listen to an AM station, you can figure out what the wavelength is using the frequency in kilohertz or times 10 to the 3 hertz. Okay, very, very good. We have taken a look at a way of graphing the wave at a particular time and looking at variations in x, and we looked at what a particular point on the wave looked like as it moved up and down for different times. Is there a way that we can graph the wave for different positions and at different times? How might we do that? Well, let's try and do it. Let's take a look at that and see how we can figure it out. Let's imagine that at some initial time t equals 0, we make a graph of our wave with the displacement y, whatever the disturbance y variable is, and we're going to graph it as a position, a function of position x. And let's imagine we're looking at one particular maximum. So we've got the wave going up and down, and let's look at one value of the maximum. Let's imagine that the maximum value occurs at some value x equals x naught. So this is x equals x naught, and we get some maximum value. Let's imagine that this function we could say is y is some function y1 of x. That's what this function is. And we know that y1 when x is equal to x naught. In other words, y1 of x naught is a maximum. Okay? So when we stick in x naught into our function y1, that's when we get this maximum value. Now let's imagine we wait for some time t. What's going to happen? Imagine that our wave is moving. At some later time, our maximum, let's say, has moved over to here. So there's our new maximum at some larger value of x. Well, what's the larger value? Well, if we wait some time t, if our wave has some speed v, then the distance it has moved is v times t. So that's going to be the change in the position. It's going to have moved a distance v times t. In other words, this point will be x naught plus vt. So x is equal to x naught plus vt at this point. But we want, when we put this into our function, we still want the value of the function to be a maximum at this new point. But we know that the function is a maximum when the argument is x naught. But how do we make that for different values of time? Well, we can see that x naught is equal to x minus vt. So if we put in here y1 of x minus vt, that whenever x minus vt is equal to x naught, we'll get a maximum. But we can put any values of x and t in here. We can look at other values of x over here. We can look at for earlier or later times. But we know that when x minus vt is equal to x naught, we're going to get that peak and whatever shape of the function that we put in there. Well, very, very good. That's a very general way of writing it. And notice that when we assumed the wave was moving to the right, in other words, when v was positive, we end up with this form, x minus vt. What do you think we would have if we had a wave moving in the negative direction? We would have x plus vt, or if v were positive, plus vt. If v is a negative quantity, then it would be x plus some number times t. But so positive v then gives us a wave moving to the right. Negative v gives us a wave moving to the left. Okay, very, very good. How can we change this function y so that we can have any kind of shape we want, any kind of variation in t? Okay, let's take a look at that. I've written down the result here, but we're going to take a look at it and see why it makes sense. What I've written is a function of y, the oscillation variable, that's a function of x, position, and time t. So we can figure out what is our variation from equilibrium at any position we want, at any time we want. Well, we've got some amplitude a, whatever the amplitude is, times sine, assuming it's a harmonic wave. And then I've put a constant in front of the k and a constant in front of the t. So we've got kx minus, and that minus, remember, tells us we've got a wave moving in the positive direction, assuming omega is positive. Let's see if we can't figure out what these two variables mean, the k and the omega. Well, for x, if we increase out, whoops, sorry, I wrote this as a function of t. I meant to write this as a function of x. If we increase our x variable, so increase x from some value to x plus lambda. So let's go from some value x to, this is x and this is x plus lambda. In other words, so looking at a constant time, so minus omega t, that will be a constant value. So if we go from kx to x plus lambda, we expect that to be an increase of the argument of an amount 2 pi, right? So to make one complete wave, the argument of the sine has to increase by 2 pi. So this must be equal to kx plus 2 pi, an increase of x by lambda means an increase of the argument by 2 pi, so that we will go through one complete wave. Well, what does that mean then? We've got kx plus k lambda equals kx plus 2 pi. The kx's cancel. Whoops, I'm sorry, I said kx, but k lambda here. So that k is equal to 2 pi divided by the wavelength. 2 pi over lambda, which tells us the change in phase per meter of the wave. This is called the wave number. And we see that k is related to the wavelength, but it basically tells us what's the change in phase, 2 pi radians, per meter, per length, per standard length. We know the length of the wave is lambda, so what's the change in phase in radians per meter? Okay, there's the wave number. Great. Now, what's omega? Well, we've seen omega before. We expect to get something very similar that we saw before, and we will. Let's do the same kind of trick. Let's wait some amount of time for a complete wave to pass by. Well, what's that time? That's the period t. So if we go from omega times t plus the period, we expect that to be, again, an increase of the phase of 2 pi. So this should be equal to omega t plus 2 pi. So what do we get? We get omega t plus omega capital T, the period, equals omega t plus 2 pi. The omega t's cancel, and we have omega equals 2 pi over capital T, or the period. And again, what does this tell us? Omega tells us the number of radians per second that the wave has. And that's exactly what we talked about before. That's the angular frequency. Great. We can also relate that 1 over t or t is 1 over the ordinary frequency f, so 1 over t is f, so we also have omega equals 2 pi f. The relationship between the angular frequency and the ordinary frequency. Okay, great. This is a way then that we can describe a traveling sinusoidal, traveling harmonic wave with a sinusoidal form. It is y as a function of x and t is equal to a, the amplitude, sine of kx minus omega t. Okay, very, very good.